Welcome everybody to Duke Spark seminar. Duke Spark. Our goal is to advance the science of AI in medical imaging, and here in our monthly seminar, we're sharing the advances of AI in medical imaging and radiology around the world. You can find us here. It's our website. Follow us on LinkedIn and Twitter if you like updates on what we're doing and future seminars. We have some exciting ones coming up. Also, we will share this on YouTube. So if you are watching this on YouTube, follow us for more content will be coming. Today, I'm happy to welcome Dr. Xiaoxiao Li. She is an assistant professor at the University of British Columbia and has some exciting research to share with us. Welcome, Xiaoxiao, and please take it away.
Yeah, thank you for the introduction, Dr. Mazurowski, and thank you for providing me this invaluable opportunity to share our recent work at Duke Spark seminar. So let me try to share the screen. I don't know whether it can work, but so can everyone see my slides well?
I can see it, yeah.
Okay, super. Let me turn on the laser. Oh, the laser didn't work well. So let me try it again. Okay, here we go. So again, it's my pleasure to present our recent work on synthetic data in longitudinal imaging, continual learning, and federated learning for healthcare. And this is my very first time to present this series of work, and we just started to explore the application and innovation of synthetic data for healthcare recently. So hope this presentation will motivate some thoughts around this area, but definitely I feel like there are much more to go. Without further ado, let's start the main content. Firstly, I want to briefly introduce the background of deep generative model. Before that, let's quickly talk about the needs of synthetic data. So I believe many of you are working on medical data. If we compare medical data versus natural data, for example, medical image versus natural imaging, medical data suffers from two issues. First, it contains small data, especially for rare disease and longitudinal data. Here are two comparison examples. So we know that ImageNet, it contains more than 1 million of samples. However, if we look at the common medical data sets, such as this cardiac data set ACDC, it only contains hundreds of samples. This is not the single sample. Actually, if you look around, that's very common. On the other hand, medical data suffers more from the data privacy regulations, such as HIPAA or GDPR, make it very difficult to be shared across different institutes. This is very different from the natural data, where you can easily download the natural data from the internet. Due to the small data issue and the data privacy that handle the data sharing, many people think about how can we use generative learning to generate more synthetic medical data. Talking about generative learning, it's a learning process to teach neural network to sample some fake image. Typically, we offer some samples from the real data distribution, and we sample some instances from this distribution to train a neural network. Then the neural network try to mimic the distribution of the real data distribution and sample from that estimated data distribution. Noting that we are using the word of sampling rather than reconstruction, because there is no guarantee that, and very impossible that you will generate some fake data that's very similar to the real ones. So before I go further, I wonder whether generative model is something that widely known from the audience. If not, feel free to put a crying face to the Q&A box. or in the webinar chat. I haven't received any crying face, so probably I will move forward. In this talk, I basically want to introduce the usage of two types of synthetic data. One type of data, which is fine-grained synthetic data, as we can see from these 5 figures, they are quite realistic and it's more like art. So I call this kind of fine-grained synthetic data as strong data synthesis. For example, we used OpenAI DALL-E 2. Later, I will introduce more about the technique. Another type of synthetic data that has been overlooked in the field is this coarse synthetic data. I also call it as weak synthetic data. As you can see, they have very low fidelity. For example, those are the synthetic data from handwriting digits data set. They don't really look at the real image. However, they have very high utility. What does high utility mean? It means if you use the weak synthetic data to train a machine learning model for a certain downstream task, for example, classification, you still can get very good classification results. In the following presentations, I will mainly focus on how to leverage these two types of synthetic data in the application of AI for healthcare. Let me move on to the first part of the talk, talking about how to use strong data synthesis for longitudinal imaging. Specifically, I want to focus on denoising diffusion model. If this is a new terminology for you, no worries, I will cover this part. Then this goes to our first work, where we use diffusion model for 4D medical image generation, which we studied the brain aging problem. And reminding, this is an example of how we leverage strong synthetic data in medical image analysis. Before I go into the depths of our work, I want to give a brief background introduction for the existing strong data synthesis techniques. Nowadays, people typically talk about 4 types of strong data synthesis techniques or deep generative models, including variational autoencoder, generative adversarial network, in short GAN, flow-based models, and denoising diffusion model. You may be very familiar with the first 2, and then recently, denoising diffusion model became a popular deep generative model pipeline. If you are not familiar with any of them, let me quickly introduce GAN. GAN is a widely used generative model, maybe 1 or 2 years ago. It contains 2 modules. One is a generator, and another one is a discriminator. Generator takes some random noise as input and generate some fake image. And discriminator tries to discriminate whether the generated image is a fake one or real one. So these 2 modules, they train adversary, while the generator tries to generate as good as the real image for the generated ones to fool this discriminator. And the discriminator is trying to do his good job to classify the generated image as a fake one. Through such adversarial training, both parts become stronger and stronger. And at the end of the day, we hope the generator can generate realistic images. And GAN model has been deployed in medical image analysis as well. Until recently, people found that diffusion model can be more powerful than the general GAN-based model. But this is not true everywhere, because recently there's another GAN called mega GAN that contains billions of parameters, also show very good performance, which is comparable to diffusion model. But nevertheless, since diffusion model have already shown very promising future, so this talk and our work try to explore diffusion model for strong data synthesis. I want to show a few examples of what type of image can diffusion model generate. And here are 2 examples from DALL-E 2 from OpenAI. These 2 images are generated from some text. For example, the left image is generated from this sentence. A Shiba Inu wearing a beige and black turtleneck. When you input such a text into this deep generative model, it's able to generate such a realistic image for you. That's the power of denoising diffusion model. Then how this denoising diffusion model works? Diffusion models, they are trained by adding noise to the images. And furthermore, those noise are added accumulatively and at different levels. And then the model tries to learn how to remove the noise. As you can see, this process can be viewed as adding noise and then removing the noise. Particularly, diffusion model consists of two processes. The first one is forward diffusion process that gradually adds noise to the input. In this process, we start from the diffusion step t equals to 0 and gradually add the fixed noise to the image, make this kind of like corrupted image. Until diffusion step t, we have the image more like a pure noise. After finishing the first step, we move on to the second step, which is a reverse denoising process that learns to generate the image by denoising. So this step is more from t equals to capital T to t equals to 0. And in this step, we have this generative process that we try to estimate the mean value from the noisy data. And as you notice here, the noise is parameterized. And in practice, people use a neural network to estimate this noise. Particularly, people like to use UNet to approximate the noise. I want to go through the whole process again with this concrete example, how the denoising diffusion model works. And this is the original work called DDPM, proposed by Yang Song in 2021. So in such a generative process, first, we select the original image from the clean data sample set. And then we sample some Gaussian noise from our assumed distribution with the specific noise schedule. Why we have noise schedule here, as I mentioned before, we want to add different level of noise to the image, so which is controlled by this noise schedule. After we get the noise, we add the noise to the original image, and then we get the corrupted image in step 3. We input this corrupted image and the time embedding, this is diffusion step, into this UNet, and then we try to generate the output, which is the noise. As I mentioned, diffusion model try to learn the noise following a certain parametric neural network. Then we compare this noise with the real noise we add onto the image through this objective function. In such a way, the penalty will be used to update the UNet parameters. Through such a procedure, you can see that we are able to use a UNet, a neural network, to estimate noise. After we can estimate noise, we know how to remove them. So this is an unconditional diffusion model pipeline. Some of you may be interested in how can we do the conditional diffusion model, like conditional GAN, for example. I want to generate an image of a cat. Can I give the label of cat and then let this generative model to generate specific image? Yes, we can do that. So one example of making it as a conditional diffusion model is using this kind of like classifier-free conditional diffusion model, where you have some conditional term, and then you use some fully connected layers to embed the conditional terms into some vectorized representation. And then you use the representation as the input of UNet. There are many ways that you can use it as input, for example, edit with the embedding of T, so that you have a conditional diffusion model. So our first work that I'm going to introduce in this presentation is based on this conditional diffusion model using the backbone of DDPM. Specifically, the problem that we are interested in is generating the longitudinal MRI imaging, which are the 3D image that we sampled over time. The use case is as follows. For example, we have a subject who scanned his or her brain at age 18, 31, and 46. And he or she wants to know, what does my brain look like at my age 75? So this is a very useful scenario where we can predict the brain aging factor, and then maybe if we notice something wrong, clinicians can do some intervention or treatment in advance. The similar task actually exists in natural image analysis. For example, we do the video prediction, given some existing frames, we try to predict the future frame. However, noticing that such a task is very difficult in medical domain due to the following 4 reasons. First, medical image has less longitudinal data compared with the video data. Second, if you look at each time point, we have the 3D image, which means the dimensionality of the input is higher. Third, in medical images collection, we may have the missing frames or missing data. For example, this subject forgot to get the data, the brain scan at age 31. And the last, if you notice the interval between the scans, they are very sparse, so we have very low temporal resolution. Noticing this issue, my visiting student, Xiaoxiao Li, and actually his supervisor, Professor Huing-Sok, is also a visiting scholar in your group, I guess. So we came up with a solution to tackle this issue, that we try to synthesize the future brain image from the past ones. Before I introduce our solutions, I want to quickly introduce the existing solution for this kind of like future brain prediction. This is a work published in ECCV 2022. They say that if you want to predict the brain at a future age, you can do the one-to-one translation. For example, given the brain at age 18, let's use a deep generative model and then generate the brain at age 75. However, such a method may ignore the longitudinal dependency when the sequence is available. For example, the subject has more than one available image. So noticing the gap, Xiaoxiao said, looking at our data set, we have at least one image per subject during the training and the inference. Let's leverage this whole existing sequence in the generation and build a many-to-one translation model. In this case, we formulated our problem as a many-to-one translation problem to synthesize the future brain, where we can consider the temporal dependency between the source image in the sequence. So we try to build some sequence-aware generative model for data synthesis. To this end, we propose this sequence-aware diffusion model, in short SADM, which can be divided into 3 components. First, we try to tackle the sequence of brain imaging, which has 2 patterns. First, they are high-dimensional image. They have the spatial domain features, and then also their temporal data. Second, we may have some missing data in the whole sequence. To handle these 2 issues, we propose to use an attention module A here to embed such an image sequence to a conditional signal, which is a vector. This is motivated by the recent transformer-based language models. Well, typically people input a sequence of words such as sentence and then do the following natural language analysis. Similarly, we treat each image as a token and append them with some positional encoding. Noting that we have some missing data, we make some similar operation in natural language process where we use some mask token for the missing data by setting their token as all 0. Then we use the attention layer. We kind of like fuse the whole sequence into one signal, as you can see here. Given this conditional signal, we plug it into the class-free conditional diffusion model together with the noise. In such a way, we have a conditional diffusion model which can generate the future image. During the inference, we used autoregressive conditional scheme to generate the future image, which means if we have the image at age 18, we don't directly synthesize the image at age 75. Instead, we do that step by step. We first generate the image at age 31 and then age 45. Sequentially, we go towards our target. We found in such a way we can get better performance. Let's look at some qualitative results. Here, this is the source image. The top line is the ACDC datasets results, and the bottom line is the in-house dataset offered by Dr. Jia Guo at Columbia University. This column is the target image that we try to synthesize. We compare with GAN-based model, the ECCV paper, with ours. As you can see, using our proposed method, sequencer-wire diffusion model, we are able to capture this kind of like fine-grained details, which didn't do well in the comparison method. We also try to see what if we use naive methods to learn the temporal dependency for the sequence. We notice that attention plays a very important role in our pipeline. If we look at the quantitative results, while we use 3 metrics to evaluate the performance on our generation, still you can see our methods significantly outperform the other methods. This is pretty much about the first work that I want to introduce, where we leverage the denoising diffusion model for the longitudinal imaging synthesis. And the key takeaway is that diffusion model is a powerful, strong data synthesis tool, and we can leverage to generate realistic medical images. Before I'm moving on to the next part, I want to pause a little bit to see if there's any questions from the audience. Please feel free to interrupt me anytime if you have any question or if you feel like any points is confusing.
Thank you, Xiaoxiao. Yeah, that's maybe a good time to mention to the audience, if you have any questions, please put them in the Q&A section of Zoom, and I'll read them out for you. And if Xiaoxiao would like to allow some time for questions in the midst of the presentation, we'll do that. And if not, then we'll do it at the end. Thank you.
Yep. Thank you, Major. I noticed one question in the Q&A section.
Okay, yeah, this is from Hao Yu. He's a student in my lab. Is the generative model able to generate out-of-content images? For example, if all training data ranges from age 20 to 50, can it generate a new image of age 70?
Yeah, that's a very good question. That will be, I mean, it depends on whether the age at 70s is really out of range. There are some work they try to do the exploration of generative model where for your training data, you don't see such an image, or your distribution cannot quantify some image within the distribution. In this case, when you try to generate the image, it's very difficult, noting that the generative model is basically try to estimate the training data distribution using another simpler distribution. So if this cannot be mimicked then that will be very difficult. But if you're adding some reinforcement learning or the other technologies that help you to do the exploration, that's possible. So here in our case, we have these targeted images all at hand. So when we train in the model, we see those distribution already. That's a very good question.
Okay, maybe let's read one more if that's okay for now. Is from Atibar Aliyev. Is diffusion based model prone to overfitting?
Oh, that's also very good question. In general, people don't consider overfitting for deep generative model that much. I mean, especially for the generator part. In my opinion, maybe I'm wrong. The diffusion model, I don't see any overfitting issue, at least for our work, and I rarely hear people talk about overfitting issue in diffusion-based model.
Okay, so we have some more questions, but Xiaoxiao, would you like to continue and leave the questions for later, or would you like to answer them now?
Maybe I can answer them later because I have 2 more works to introduce. I want to promoting 2 more works from my students. I don't want to make them disappointed of not covering their work. Okay, so yeah, I can do the more Q&A regarding the first work later.
Sounds great.
Okay, we have talked about strong data synthesis using denoising diffusion model. Next, I want to talk about the weak data synthesis, which our group has already explored this direction for around 1.5 years. And specifically, we use a technique called dataset distillation, which probably is not that popular as deep generative model. And we show the use case in federated learning and continual learning. Again, if some terminologies are new to you, no worries. I will go over those terminologies later. So in this part, I will cover 2 works. One work is under review, and another one was accepted by MICA 2022. Those are the usage of weak synthetic data. Maybe I should talk about why we are interested in federated learning and continual learning, these 2 learning frameworks. In the traditional machine learning, we can share the data. We always first collect the data into a data center and then train the machine learning models. However, due to data regulations, in many scenarios, data cannot leave the institute. So this raises a question of how to train machine learning models without data sharing. There are 2 frameworks can tackle this issue. One is federated learning. Well, data are kept into the data collected location. However, some models that train on those data can be shared. The second learning framework is called continual learning, or if you are more familiar with transfer learning, that's something similar, where you train the model using those data locally again, and then only carry over the model rather than the data. In this case, as you can notice, no data is shared on the fly and only model will be shared. Now I want to introduce the weak data synthesis technique we use in these 2 learning frameworks, which is called data distillation. And data distillation aims to generate a small informative data sets from an original large data sets. This is the diagram that people originally used to propose this data distillation framework. For example, you have the ImageNet data sets contains millions of data, and then they say we can compress the data into 5,000 data points. And then we use these 5,000 data points to train the machine learning model. They can have the similar performance as if you train the machine learning model on the original large ImageNet dataset. And also, you may notice that if we want to guarantee the similar performance, we have to do the dataset distillation with the downstream task supervision. This is very similar to another idea called coarse set selection, where you want to select the most informative subset from your large data samples, and then ensure that the small data set still can perform as good as the large one. So the core idea of data set distillation is condense a small data that can present the whole original data sets and keep the utility. Noting that the primary goal is to keep the utility of the original data sets. And fidelity or realisticism is not the main optimization goal of using data distillation to generate synthetic data. So we call it as weak data synthesis. It doesn't mean that this generation technique is weaker than diffusion model. It's more like the purpose is to generate weak data to make them not as real as the original ones. There are two popular schemes to do the dataset distillation. One is called distribution matching. The objective function is to match the embedding similarity of the real data and the synthetic data. We say that if a synthetic data is a good approximation to the real data, its embedding, let's say, the embedding after passing the data through some neural network layers, it should be similar to the real data ones. Another technique is called gradient matching. Well, here we leverage some gradient of particular neural network. So we use the same loss function, the same neural network, and then we calculate the gradient with respect to the real large training data and the synthetic data. And we hope that the gradient of the loss with respect to these two types of data on the neural network should be similar. This is also very intuitive. Again, you may notice that when we use the gradient matching to update the synthetic data, we also count in the cross-entropy loss. For example, if you use the classification as the downstream task. This means when we do the dataset distillation, we leverage the downstream knowledge. Here are the interesting observations if we do data synthesis by dataset distillation. Here are 4 sets of images. The most left one is the original real data. This one is the selected data by coarse set selection. This set of image is distilled data using distribution matching. And this set of image is distilled data using gradient trajectory matching. As you can see, these synthetic data, they are visually very different from the original data. But however, if we use this type of synthetic data to train the machine learning model, for example, classification, they can get very high accuracy, almost the same as using the real data to train the classifier. Noticing such a good property, my student Jing Huang proposed this FedLGD, Federated Virtual Learning Heterogeneous Clients with Local Global Distillation work, which is in collaboration with NVIDIA. He saw that whether we can use data distillation to generate synthetic data so that in federated learning, we can leverage the synthetic data of training. If you are not familiar with federated learning, let me quickly go through the pipeline. For federated learning, we assume that multi-parties are joining the collaboration. Assume that we have hospital 1 and hospital 2. Each hospital has their protected data that cannot be shared to anywhere. They train their local model using their protected data, and then they share the model to a central server. The central server aggregates the weights and then broadcast the updated weights to the parameter model for their local updating. Through such a pipeline for many iterations, different hospitals can leverage the knowledge from each other without sharing data. As you can see, they share the model weights instead. However, the federated learning pipeline itself does not guarantee any data privacy. I will talk more about it later. And also, as you notice, since we use data collected from different institutions, the data cannot be shared with each other, which means we cannot do normalization in advance. So data heterogeneity is another big issue. Now let's look at what's the data privacy issue in federated learning, although the data is not shared. There's kind of like data privacy leakage induced by gradient inversion attack, and this is found by Dr. Hans group in 2019. They say that, let's assume this is a federated learning participant and they share the model parameters to the server. And we have some malicious attackers in the federated learning pipeline where they can take the model parameters into their reconstruction pipeline. They propose some loss functions so that, assuming that you are using this table as training data to train your federated learning model, and then they use a certain loss function to get the updating for this random initialized image. They say that we can recover your training data by purely using the gradient of your model, which means although in federated learning, we share the model instead, malicious attackers, they can still reconstruct the training data. That's really horrible. A recent work proposed that if we can use data distillation, generated synthetic data for training, they found that it's more difficult for this kind of like reconstruction attack and provide more empirical privacy benefits. Another issue we mentioned in federated learning is data heterogeneity, include the distribution shift. For example, if you look at the brain imaging sampled from 4 different centers, the density distribution from different tissues can be very different. Or if you consider the class distribution of different clients or different centers, they can also be very different. Using data sets distillation, you can generate synthetic data and generate class balanced one. However, it does not tackle the distribution shift issue. Furthermore, we notice another trouble. If we look at the federated learning embedded feature for 2 local clients using the classical federated learning that trained use the real local data, the blue dots are from one hospital, and then the red dots, the red circles are the embedding from another hospital. They have this kind of like mismatch due to the data heterogeneity. We surprisingly noticed that if we directly use the synthetic local data in federated learning, such heterogeneity can be amplified. This brings in more trouble of optimizing the federated learning. However, this problem was tackled in some classical federated learning framework where people can introduce some global data to calibrate domain shift. For example, here we have 2 clients, which are circle and a triangle. And then people assume that we have some global data at the server, which can be served as the anchors. If we don't use this global model for calibration, the embedding of 2 clients may be far away from each other. And people notice that if we force the embedding of 2 clients to be similar of the anchor data, which is from the global data, such collaboration can make sure those shifts can be mitigated. By leveraging this technique, Jean think about how can we get some global data in our framework? Recalling that in this framework, we don't want to use the real data. Can we generate any synthetic global data to help with the calibration? Then we come up with this FedLGD framework. It's a very complex pipeline, and I try to decouple it into several steps. First, we have the simple setup as the classical federated learning, where the local clients have some local private data. The first step is to generate the synthetic data for local model training. In this case, we leverage the distribution matching as we introduced earlier. We have the neural network. We want the synthetic data have the similar distribution as the real data. In such a way, we use the distribution matching loss to update the local virtual data or local synthetic data. After doing this step, we submit the gradients to the server. And the server can further use the gradient matching technique to update the global virtual data. This is about the synthetic step. And after the server updates the global virtual data, they send the virtual data and updated the model weights back to the clients. When we have both local virtual data and the global virtual data, we conduct the normal model updating in federated learning. where the local model will update the neural network with the supervised label and share the model updates to the global server. And the global server perform fed average, which is the simple framework that I introduced earlier, to update the global model and then submit and broadcast the updated global model back to a local client. Noticing that we have two steps. One is local global distillation, which is a synthetic step. And another step is local and global model updating. In such a way, we formulate two stages in our framework. The first stage is warm-up. So for a certain warm-up iteration, particularly we set the iteration as 10, we perform step C and D on the local client. Particularly, we perform the local virtual data updating and the local model updating, and then submit the model gradients to the server. The server receives the gradient, then perform the global virtual data updating and the global model updating, and then broadcast the model parameters and the global virtual data back to the clients. After warm-up, we go to the second stage, which is federated learning with virtual data. This is very similar to the traditional federated learning. The only difference is that we use virtual data to train the model rather than the real data. As I mentioned earlier, if we just use the virtual data to train the model, we notice that we have very severe feature shift from different clients if the data itself is originally very heterogeneous. Noting that in the previous data synthesis step, we also get some global virtual data. So Jing proposed, let's leverage this global virtual data in our local updating, and then try to force the local virtual data embedding similar to the global virtual data embedding, which this kind of distance can be used as a regularization term in your local model updating loss. By leveraging this regularization, we can align the features from different clients. Maybe you are curious about what the global virtual data look like. As I mentioned earlier, using data distillation to generate synthetic data, they may not look as the real data. For example, the top ones are from the handwriting digits and data synthesis results, and the bottom ones are the retina data we use for glaucoma and the non-glaucoma classification. They are far away from the real image. But surprisingly, we notice that leveraging those synthetic data for the federated learning training, we can achieve particularly better results when we compare with the other federated learning strategies. As you can see here, we test our method on two different model architectures and both significantly better than the comparison methods. Now you may be curious about the privacy issue. As we mentioned, we want to use virtual data to handle the data privacy issue. Let's recall that in the client side, we only update the gradients to the server. That's the same as the classical federated learning. Furthermore, those gradients are with respect to the virtual data rather than the real data. So here we do a very quick privacy test using membership inference attack, and then we got such a results. How to interpret the results? If a model is privacy preserving with respect to this particular attack, its performance should be aligned with diagonal line. As you can see, using our proposed method, we have the blue line that's well overlapped with the diagonal line. However, if we use the traditional classical federated learning strategy, and we end up with this blue curve, which is shifted away from the diagonal line. If we train longer, such a shift will be more severe. Since I only have around 10 minutes, I want to introduce one more piece of work. I don't want to disappoint another student, and I'll leave all the questions at the end. After talking about federated learning, I also want to briefly introduce the continual learning. It's very similar to federated learning that we don't want to share data when we update the model. My master student, Sana, she proposed a technique called class impression that we use the synthetic data in the continual learning to tackle a few issues. So when we consider continual learning, this special learning framework, in the real life, we don't have all the data at hand when we train the machine learning models. And typically, data, they arrive over time. For example, originally, we have the binary classification trained on two kinds of data. And then we deploy this binary classifier. Somehow, at a certain time point, we have the data samples from a new class. We want to adapt this binary classifier to a three-class classification problem. However, we don't have the access to the original data points. This is common when we consider the data privacy regulations. In such a case, we need to consider two tasks. First, how to extend the knowledge over to the new introduced data sets. Second, how can we preserve the old knowledge so that the new classifier that we train still can do good job on these old data distributions? There are a very severe challenge of tackling this issue, which is called catastrophic forgetting. And this is a well-known problem in continual learning, where when you adapt the old classifier to the new data, you may try to overfit to the new data and make the old data's performance bad, especially when you don't have access to the old data. To tackle this issue, Sana proposed that let's generate some synthetic data for the old classes, so that when we adapt the old classifier to the new classes, we still can train the model on three classes of data rather than only one. To this end, she proposed class impression, which contains two stages. First, we take the old classifier, and then we try to do kinds of like data distillation to generate the synthetic data for those old classes. As you may notice here, these synthetic data, they may not look pretty beautiful, especially later we see this the real data from the future classes. After we generate the synthetic data from the old model, we combine the synthetic data and the label the new data together to train the new classifier. Here, Sana proposed several novel losses to make the classifier perform better. And as you can see from this figure, the appearance of the synthetic data and the real data may not be exactly the same. That's a common issue for weak data synthesis. So Sana proposed to use some unlabeled testing data together to train this new model. Particularly, three novel losses are used. The first one is cosine normalization cross entropy loss. We noticed that if you directly use the cross entropy loss, the softmax score may be biased to the new class because they look more real. So we propose to use the cosine normalization to make the loss score more balanced to different classes. And then the decision boundary can be improved in such a way. The second novel loss is margin loss, that we try to push the decision boundary far away from the real data sample and the synthetic data samples. And lastly, noticing the domain shift between the synthetic data and the real data, we leverage the unlabeled testing data, we generate the pseudo label, and then we claim that the data samples within the same class, they should be closer to the data samples from another class. By incorporating those novel two-stage design and these novel losses, we get pretty good results compared with the other continual learning strategies. Here is the comparison results that our method is in this blue curve. And compared with the other data-free continuous strategy, we perform much better in this 5-class classification task for cardiac V classification. We are slightly better than this non-data-free method, but anyway, they save some data. They kind of like be easier than our proposed strategy. As Senna proposed several novel losses in this framework, we also did an ablation study, noticing that although missing some losses, the performance may drop, but still we may perform better than alternative data-free continual learning strategy. Let me quickly summarize today's talk. There are two big issues of medical data analysis. One is small data, and the second is data sharing. We propose to use strong medical data synthesis to assist diagnosis and understand the biological pattern. For example, we use the denoising diffusion model for 4D brain imaging synthesis. We also propose weak medical synthesis to help improve machine learning performance for medical data analysis. For example, handling the heterogeneity and the privacy issue in federated learning and continual learning. There are many other interesting directions of data synthesis in medical image analysis, such as super resolution, contrast-free image generation in clinical applications, which can reduce the imaging cost and reduce the radiation exposed to patients. Regarding the machine learning problems, people can further improve the privacy preserving, efficiency, and the robustness of the generative models. Today, I briefly introduce 3 works led by my 3 great students. And also I want to show my acknowledgement to my collaborators who greatly contribute to those work. And this is the group photo. If you are interested in learning more about our group, feel free to scan this QR code. Just take 1 more minute to introduce some other work, because I think this is a good opportunity to call for collaboration. So I want to introduce some other topics in our group that's not covered using 1 minute. We are also interested in representation learning, for example, how to do the fire representation learning and the robust representation learning. We have done lots of work on federated learning, focusing on heterogeneity, optimization, imperfect supervision, and the privacy preserving. We are also interested in healthcare application, including neuroscience and new molecular analysis, and so on. So that's pretty much about this presentation. And thank you so much for your attention. I'm happy to take questions afterwards, but I know that I'm running out of time.
Yeah, let me actually read the questions from our audience. If I have, I'll have a question for you if we still have time for it. But I want to make sure that our audience has the opportunity. So a question from Hanchua Go. May I ask how you compare your method with diffusion-based methods? You directly use their methods generating 18 to 61, or you compare them also in a step-by-step way?
Yeah, that's a very good question. I think this is about the comparison with the ECCV paper where they do the one-to-one translation. So here in comparison, we follow their original setting. We didn't do those kind of like autoregressive generation. We just map the age 18 to 61 in the comparison. Yeah. But for ours, we did that autoregressive generation, which means we always generate the next step image before we go into the target.
Okay, thank you. A question from Nick Cones. Comparing to GANs, is the sampling/inference time of DDPMs a significant obstacle, considering that you need to do around 1,000 forward steps with denoise versus the single forward pass of GAN?
Yeah, I think Nick raised a very good question. When we talk about good performance of diffusion model, actually I kind of like hide the downside of it, which is the computational cost. Yes, you are right. The sampling inference time of DDPM is really annoying, and also it requires more computational resources. So particularly in our work, we have to downsample the input by 8 times to fit into the GPU. So this is some kind of drawback compared with GAN. However, some technique can be used to tackle this issue. So if you have heard about latent diffusion model, where people first use some VAE to embed your input into a latent space, which has much smaller dimensionality, and then that can be served as the input of diffusion model. I think many nowadays work, they try to leverage such a technique to handle the computational issue. However, regarding your problem of sampling and inference, also there's a line of work try to tackle this issue, how to make sampling and inference more efficient. Yeah, that's a very interesting future direction in diffusion models.
Thank you. Okay, and a question from Richard Chu. How can we ensure that the synthetic data does not leak private information about the original data? It seems possible that some attackers may reconstruct the original data from the synthetic data. In that case, sharing the synthetic data would should also be avoided.
Yeah, that's a very good question. So I didn't put this slide. In general, I mean, we cannot guarantee that synthetic data does not leak any private information if we don't have any privacy preservation technique. So one of my students is trying to introduce differential privacy in data synthesis. In such a way, we may have a statistical privacy guarantee. But in general, through some empirical attack, people notice that either we use membership inference attack or using gradient inversion attack, it's much difficult if we train the neural network using synthetic data. And another thing that I want to claim is noticing that for a deep generative model, it's not performing data reconstruction. It's basically try to mimic the complex distribution of your input X using some simple distribution. So at the end of the day, you get the distribution and then you do the sampling. Only if you sample 1,000,000 times or as many times as possible, you probably will get the sampled image or synthetic image that's almost the same as your real image. Yeah, it's a solvable problem, but maybe NP hard. Yeah, I hope I addressed your question, but that's a very good point. Using synthetic data itself, there is no theoretical privacy guarantee.
Yeah. Thank you. And somebody was asking, that question doesn't appear anymore, but somebody was asking whether the presentation will be made available, and the answer is yes. We will put the presentation on YouTube. And so a last question from me, a general question. Do you think that practically federated learning will be a common and important way of training models? So, you know, for models that actually are developed and then implemented in clinical practice, do you think that many of them will come from federated learning?
Yeah, that's a very good question. Federated learning is a very popular research topic nowadays, but when people talk about when federated learning can come true to the real deployment, it seems many non-technical issues to tackle. I have to say, I mean, over the past 3 or 4 years, many novel and reliable federated learning framework and algorithms have already proposed. But if we look at the infrastructure, for example, if different hospitals, like say Vancouver General Hospital and some hospital at Duke University, we want to do the federated learning, what kind of infrastructure that we should rely on? For example, we have a server here. What should be server? Should we use AWS, Azure Cloud, or we rely on one institution's internal HPC as the server? That can be an open question. But regardless, I feel like federated learning has drawn more and more attention to some data sensitive field, not only for healthcare, but also in, let's say, financial industry and so on. People are considering, can we really leverage the data from different institutions or different data sources to improve the model training? In today's presentation, I only introduced one framework. Actually, there are many other alternatives for federated learning. But overall, I feel like this is the future. Well, we don't really need to tackle those obstacles of data sharing and go through lots of legal documents. And then we can encourage the institutions around the world to collaborate with each other, particularly the institutes in the rural area for those kind of underrepresented populations. They will be ultimately benefited from federated learning and such a collaboration.
All right, thank you. And thank you very much for your presentation. Thank you, everybody, for participating and your questions. Tune in for the next Spark seminars. Check out our social media where you can find out what the plan is for the upcoming months. And if you're watching us on YouTube, again, follow us. There will be more presentations coming. Thank you very much.
Yes, thank you much. Thank you for the invitation, and thank you for all the audience for your attention. Yeah.
Great, thank you.